Good afternoon. I have a question for you. Please raise your hand if you know what is the flow stage. 1, 2, 3, 4, 5. Okay. Next time I like to see more hands. If you look it up, I think you know it is important, isn't it? And I wish to be able to be in this flow stage for a long time in your life. It's something very important. But to do that, you need to have some skills. Because without good skills, you cannot meet big challenges. You cannot solve some very hard problems. Because you can be in a flow stage if you can solve something what is very hard for you. But you can do it. And if you can able to do that, it gives you a great feeling, the best feeling whatever can have. Today, I will talk about, again, artificial neural networks. The reason because in this AI field, this is the most popular, most promising paradigm. That's why we have to be at least familiar with it. I don't want to mislead you. I cannot teach everything about this field because it is extremely complex. As you know, one of the most complex things on Earth is the human brain. And this metaphor, this artificial neural networks, use the brain as an example, as a model. Try to mimic somehow the brain functions. Fortunately, we live in an age when we can make extremely useful practical applications with this new metaphor. Not just dreaming in a far future to be able to do something, we can already do something extremely useful things. You can make a list, if you like, what are those applications. I showed you some of the examples in the previous classes. So, because of this, at least it is good to be familiar with it. As I mentioned last time, this is not a totally new paradigm. The people who wanted to build computers, machines, dreamed of it for a long time. But that time, decades ago, or half a century ago, the technology was not mature enough, not good enough to be able to do something useful, really useful. They was able to make toy solutions, what was fun to have, it was interesting to see, but that time it has a very hard limitations. And that's why it was not good for practical applications. But these days, most of these obstacles or limitations are gone. First, we have huge amount of data. The reason why we have huge amount of data, because this new paradigm based on data. Instead of algorithms, we need to have a lot of samples, a lot of data to be able to train the network, instead of program the network to train the network. As we learned last time, a lot of math involved in this field. It is not just a totally analog approach to do something similar. We need to understand what is the mechanism behind that, and if you want to implement it on a computer, but this is the stage today, we need to use significant amount of math. Good thing you are in this field. This is your subject. This is your profession, what you are studying for, to be able to solve this kind of information processing problems. And math is unavoidable. You need to understand things. The second question for you today, please raise your hand if you looked it up, the backpropagation method. Please do it, because it is important. If you understand how backpropagation works, the back error propagation to be precise, you will understand the huge chunk of these solutions what is on the market today. Of course, because it is so important, so hot, what I say, many people works on it. Huge companies, Google, Tesla, can name most of the big companies, can focus on neural networks because it can provide something extremely fascinating, new features, what can be marketable. We can sell it, we can use it. That's why it is very rich, the whole field. And to be able to understand all of the details, it takes many years. But since you are young, you have a good opportunity to learn it, if you're interested. If you are not interested, you will do something else. There are so many other good things on Earth. Neural networks is just one of them. but for something very important. And if you're in the field of informatics, it is very important for us. If you are doing something else, architect or mechanical engineering, it is not so important because somebody else will do it. So today, I'd like to explain to you some of the basic concepts behind that. The selection was totally for me. There is no list what should be covered in this field. As I mentioned to you, it was one of the main interests in the past decades, and my goal was here to summarize it, what I learned. And this is the result, what I can show you today. So today I'd like to cover the unsupervised training, and then I will show you some very important, interesting examples, old ones and new ones too. And when we finished this topic, I like to continue with the sensors. The reason, because the sensor is one key element for making artificial intelligence. Without good input, we cannot sense what the situation is, and we cannot react properly. If you want to react properly, meaning that smartly or intelligently, we need to sense the situation, understand the situation, and have a knowledge, formulated or raw knowledge, just data, but based on this vast amount of data, we can make some good solutions, some good practical solutions. First, what I like to go back for a second, the data, the training data. Neural networks based on data. We can name it the data science, because without data, we cannot do anything. Because we don't have equations, we don't have algorithms. We have algorithms to program it, to do something with it, but in a different sense. But we need to have a huge amount of so-called representative data, covering all of the topic what we like to cover with this new application. The first part of this is a so-called training data, this area here, from here to here. It can be represented in a two-dimensional space, meaning vector, or it can be a matrix. It can be three-dimensional matrix or any dimensional matrix, because we have a computation power to do that. Usually, we use this so-called vector input like this here. So neural networks usually looks like this, represented like this, one input vector and some output vector. This vector can be matrix and so on, but usually vector. And then we provide the input data, one of them for the very first one. And using this method, we will calculate the output. And if you have expectations, so-called targets, we can compare the result with the targets. And if we measure some difference between the expected and the real output, we can modify the network inside. This is what we can name training or teaching the network. We already know that. It is relatively simple. I name it relatively. It can be very complicated mathematically, but as a result, as a final result, it is simple. We just need to plug it into the equation and calculate the weight change. Because the way had this network change, modifying the weights, the interconnecting weights. And then, if the first sample is done, we can go to the next one, project the input data to the inputs, calculate the output, calculate the difference between the targets and the outputs, and if we sense some difference, if we measure some difference, we can go back and change something inside the network, train the network. And we can do it in a circle, long time. And when we finish the training, going through all of this data, finishing meaning that we define at the beginning some kind of stopping function, some kind of stopping criteria, when we should stop, because we can keep doing that as long as you want. But if the performance of the network is good enough, we can stop. We don't need to do it continuously. As I mentioned last time, if we would be so fortunate to set the initial connections, the weights, properly, we don't need training, because the network could do what we want it to do. This is the case when we have a trained network, and we are plugging this matrix, the weight matrix, into the empty network, empty neural network. If we can plug it in, this network already know what should know. Clear? So when we finish this training, for example, the expected performance is okay, Then we can test it. We can go back to these test samples. Those samples what was not shown for the network ever, but if we expect some good result from the network, we expect the same kind of performance using this test inputs too. If not, we need to go back to the training and keep doing that till we reach the good solution. The bad news is here that it is not 100% clear science. Scientific methods are behind that, but we are still in a early stage, some kind of heuristic stage. When we have some good ideas, we have some metaphors, we are trying those metaphors, those ideas, and if it is successful, we will keep going with it. If not, we will try something else. Maybe, hopefully, within our lifetime or your lifetime, you will have some very solid methods behind that, how to design networks. Now, these days, there is some kind of art in it. How to specify the nodes, the neurons, how many layers we have. It will be fully connected or not, it will be reverse connected, or something like that. We need to figure out many things to design a neural network. Practice shows, usually it is very successful, even though there is a lot of art behind it, some kind of heuristic methods. So, this is the first thing what I wanted to show. Let me repeat the supervised training algorithm. I hope you already know what is that. Just let me summarize very quickly. First, we initialize the weights. We need to give some initial weights in it. It can be a random procedure. If you have some good idea how to put it in, we need to use it. But usually we don't have. We need to put some data in it. I mean numbers, because these weights are numbers, from minus something to plus something, depending what limitations we set for the weights. And then we will start with the first training data, calculate the outputs, compare the output to the target values, and if it is needed, we need to adjust the network. And we need to test it using the test data, and then, if the performance is not good, we need to continue this training. Unfortunately, there are some bad situations, but we cannot achieve a good performance. I will show you why. Very simple reason behind that, but we will understand it today. So, if this is the case, we cannot achieve a good solution, we need to start it from scratch or starting from the beginning. We need to redesign the network, set the new weights, set the new layers, and test it with the new or the same training data. And if we are lucky, next time we will have a better result. Soon you will understand why it is that. Somehow going to the math part, we can define the error. For example, the very simple way to define the error, calculate the difference between the target values and the output values. Since it can be positive or negative, it's a good idea to have it squared like this here. And we need to summarize it for all of the training data and for all of the outputs. This double sum represents this. Since we already know that, the way how to calculate the weight change, we need to differentiate the error function. This is the error function. We need to have a differentiation. We need to differentiate it because we like to see what is the gradient of this error surface. Because the goal is to go down on this error surface. We have a given situation, given data. On this given point, we can calculate the gradient of this surface. And then we can step back a little bit, going down a little bit on this gradient. Because we are doing this, this square is okay because we can square this out, bring this square out, and a half times square will be 1, so it is easier the equation later on. This is a reason, another reason why we have to have squared. Because of that, the motto is here, we need to change the weight proportional to their contribution to the errors. This is the simple explanation. More mathematical explanation, we need to calculate the partial derivatives of the error function relative to the weight functions. Clear, isn't it? So this is a gradient method, because we are calculating the gradient, the slope on this surface. And just going back to the real basic things, we have two different types of weight adjustment methods. One is the so-called supervised training. In this case, we have expectations. We have target values. Based on these target values, we can calculate the difference. Based on difference, we can calculate the error. And if you have an error function, we can calculate the error function dependence on the weights, and then we can change the weights. But there's another method that I like to cover today, unsupervised way. We don't have target values. We can feel it's kind of magic, how to change something we don't know what to expect. But we'll learn how to do that. At least one basic model, the very basic model. My impression is that there are many, many models in this field. I cannot cover it. If you're interested, I will point several literature to go in it if you like, and you can learn it by yourself. There were two basic rules, very important to understand. The very basic rule was the so-called Hebb rule, this one here. It means that if you have two interconnected neurons, and there is a weight between these two, meaning that how this I neuron can influence the J neuron. It is a number. It can be negative or positive or zero. If zero, there is no influence. And then it was Hebb idea that if these two neurons going together, active in the same time, the interconnection weight between those will be increased. So this is positive, this is positive. The original weight between these two in a given moment will be increased. There is a factor here, the little factor, so-called learning factor or coefficient, but is a smaller number than 1 because we don't want to jump too much. We don't want to change this interconnection so much, just a little bit, just a tiny bit. Because what is our understanding? We are on an error surface. We don't want to jump too much on the error surface, just a little one. That's why we have this coefficient here. Sometimes, usually between 0 and 1, usually closer to 0. Clear? And there's another method, other basic rule, what is in a core most of the neural networks, so-called the delta rule. When we have target values, we can calculate the difference between the target value and the output value, and then the weight modification in a given moment will be something similar than here in a Hebb rule, but instead of having only the output of J, we have the delta of the J, the difference between the target value and the output value. If the output value is smaller than the target value, meaning that we need to increase the output, the J output. That's why this will be positive. If it is negative, meaning that the output is larger than the target value, we need to decrease the weight, because this is a way how we can decrease the output of the J. Clear? So, this is the two basic rules what good to keep in mind, because it is usually in many, many other learning algorithms. And here was the basic situation when we have not only two-layered network, one input element and one output element, we have a multiple layer network. It is a feed-forward. It's called a very simple way to do networks. It's a feed-forward network, input layer, output layer, and some so-called hidden, because it is not visible from the outside. It is clear that when this Rosenblatt in the 1950s introduced his perceptron, he was able to change the weight inside the network only if it had two layers. One output layer, and because he was able to calculate the difference, based on the difference he was able to change the weight for those neurons. But he had no idea how to train the network if there's a hidden layer inside, because he had no clue how to change this weight, this one here. And the big breakthrough, big achievement was in 1982, when these two guys, Rumelhart or three guys actually, published a very short paper in Nature. I encourage you to read it. To be able to do that easily, let me show you. I usually try to put together the recommended readings for you, like this here. The very first one is this learning representation by backpropagation errors. This is the basic article. If you will go there, you can read the article. You can go there and see it. It is, I think, less than 4 pages. Not an easy reading, but you can do it. Since you have math background, you can do it, and I encourage you to understand it. I think it will pay you back in the future if you will understand the backpropagation in details. And the starting point is this basic source. It was the first publication in this field, and many, many others followed. Many interesting new modifications and so on. And so this is what I like to mention to you and encourage you to do it. So going back to here, this guy published a very interesting idea. It was some heuristic idea. All of us would know if we would be in the same situation, maybe wouldn't recognize it. They recognized it. What was the idea here? They had to calculate the error function, that error function what I just showed you, and they had to somehow calculate the partial derivatives of the weights, related to the weights. But unfortunately, the previous step function what the perceptron used, it was not differentiable. Because of that, they introduced the so-called sigmoid function, this 1 plus a ad x something like function. Because of that, it is easy to differentiate, easy to calculate the partial derivatives. Based on this modified step function, it was not a step function like that, it was some kind of smooth step function. It is called partial exponential function in a neuron. It was differentiable. Since it was differentiable, I was able to do that, and this is the complicated thing what I showed you. Let me ask you, please raise your hand if you started to understand this one here. Thank you, glad. If you have a question, ready to answer. Happy to answer to you. Find me, and I'll be happy to answer to you. I really hope there are no errors in it. I try to clean the errors from it time to time. The basic point was here. This is the basic output here, J and I. We can calculate the weight change based on the partial derivatives of the error function. Since the error depends all of these elements inside, the summation, or called activation, and a transfer function, then we need to use the chain rule. To be able to do the chain rule, we need to do these three elements, one element, second element, third element. And these elements can be figured out in the followings. Based on these following things, we can plug into this one, that one, and this one. And this all together, these three elements all together will give us an equation how to do it. The good news is here, if we have this equation, we need to plug in the numbers and we can calculate it in a microsecond or nanosecond. And most of the neural network applications these days utilizes this method. So that's why it is so important to understand. Finally, we have these equations, these ones here. It looks scary. Just look at it, look it up, look at it. But if we understand what is behind it, it's very easy. Just like usually, if you know the solution for the math problem, it is a piece of cake. If you don't know the solution for the math problem, it is complicated and we don't understand. We could have a chance to understand this using this previous math. So because of that, we have a method how to adjust the network inside. And then the problem is here it is a gradient method, meaning that in a given point we will calculate the derivatives of this error function. It is kind of parabolic function because of the square in it. We can calculate this gradient and stepping back a little bit from this point to that one, somehow minimizing the error. This is the goal. But the problem is the following. If we have this method, it works fine if the curve is something like this here. We can calculate in this given point, this is the gradient, and we can step a little bit backwards, somehow down in an error surface. No problem. But the problem is the following. If the situation is like that, we will calculate the derivatives in this point here, but it's 0, because it is parallel to the x-axis. If it is 0, meaning that the modification is 0. So even if we're working something, calculating the error, we are not changing the weight at all. Unfortunately, we cannot predict where we are on the surface. That's why we are calculating that and try to figure out what is there. If this is the situation, it will not change the weights, and we can keep doing the training forever, we are not achieving better results. If we are not lucky, this is the situation. To overcome this obstacle, this problem, there are many solutions for that. I like to list some of them, some important, interesting ones. The reason, because it has a transfer for us. We can use it in many other situations too, not just for neural networks, in some other life situations too. For example, one of them is so-called a momentum. Just let me explain to you what is that. Instead of using just a delta, the modification related to the partial derivatives, we are using the previous step delta too, not just the given delta, the previous delta. If the previous delta was not 0, we still have some modification. To understand the situation, for example, if you like to go sledding in a snowy winter, you will sit on a sled and you will go down on a slope. And if you will have a horizontal area there, you can have a good chance to stop, because you don't have a momentum to go further. But if you have a speed, definite speed going on this polarized area, you can go further. This is the same here. If we are using the previous delta, what has different value than 0, even if in a given point it is 0, we can still keep doing. Clear? It is one good idea. Just have one small modification for the weight adjustment to incorporating the previous data in some portion of it. If it is clear, please raise your hand. I like to understand. Thank you very much. Great. The second is the descending epsilon. Very important idea, interesting idea. Instead of training all of the weights inside the network, it can be a time-consuming and very computationally intense procedure. Instead of changing all of the weights, we will calculate the given output for the given training data, and if the error is larger with some value, some threshold, we will modify the weights. But if it is not larger, we don't change anything in the weights. Just go to the next data. Let me give you a very interesting example. If you study, for example, for the exam, and it is a very important exam for you, so you're not based on your luck or your pocket knowledge, what you can use in an exam, you want to study it. You can at least follow two different extreme paths. One is to start from the beginning and start regularly all of the questions and then finally reach the end. For example, here is the list of questions that I put together for you. Altogether 133. As I mentioned to you in the very first class, if you will be able to answer these questions, you will definitely pass this course. Because in a test, about 4 weeks from now, I'm going to ask maybe 10 of those questions from here. You need to be able to answer it. You can make some pocket knowledge, but I don't encourage you to do that because you cannot use it in the future. You will lose it, you forget it. Better to understand it if it is in your head, and if you are making connections to other things in your life, you will remember those topics, and I think it is important. So, if you have this list of questions, you can start with the very first one and say, okay, what is intelligence? I know something about it, I will leave it later. And I go to the next one. What is the artificial intelligence? Oh, I know something about it, I will go later. And going till the point when you find something but you don't know anything about it. So your knowledge and the real expected knowledge, there's a big difference between that. The error is big. So you will study that. And if you have some clue what is that, you already have something idea what is the answer for the specific question, you will go to the next one. If you know something about it, just skip it. And find the next one, but you don't know anything about it. So when you reach the end of the questions, you go back again and change the expectations. What expectations you have to be able to answer these questions. And you are going gradually. This is called the descending epsilon. Clear? I think it is a good idea to do that because it saves a lot of time for you. And you will cover the whole material evenly. Maybe not perfectly, if you are maniac, just like I am sometimes, You can start with the very first one and learn as much as you can about it. But time is always limited, and before the end of the exam, you will reach only the half of the questions. You don't have time for the rest of them. So you will have a perfect answer for the first ones, but you don't have anything to the rest ones. It's a problem. I don't think it's a good method. I would rather encourage you to do this descending epsilon, and this method is utilized in neural networks too. Instead of changing everything and all details, that we change the weights only if it is really needed, if the output is something totally wrong. Clear? Next one is the simulated annealing. Great idea. To tell you what is that. Way back, 1,000 years ago, when they started to use the iron for making swords or axes or something like that, tools, they figured out it is very well produced if it is hard. To be able to make it hard, they had to somehow so-called temper it, meaning that heating up in a very high temperature and cooling down very quickly, putting into the oil or water or sand or something like that. Instead of just leaving in the air to cool down gradually, they put it into some so-called more aggressive coolant, for example, into water. If you put it into the water, this sword or this axe was so-called tempered, meaning that it became very hard, sometimes brittle, very, very breakable. And instead of having a very breakable sword, they figured out a method what to do, heat it up again, but not as hot as it was before, and let it cool down gradually, slowly. This is called annealing. This method is called annealing. And doing this properly, it was a kind of black art also to do that. It was not a total scientific way back. Now it is science these days. They can measure the temperature very carefully. They can heat it up very carefully and given temperature. But if they will cool it down from this second hot stage, it will somehow take out the tensions from this iron, from the steel. And then it can be hard enough, but not breakable enough. Not much breakable. Clear? And to do that, there is a physical process behind that, adding some heat to the frozen elements into the tempered sword. To giving a heat is some kind of noise, because the heat is somehow moving the particles inside. The same method can be utilized in neural networks too, strange enough. It is called simulated annealing. If we stuck one of these inflection points using, for example, this backpropagation method, what is a gradient, it will stuck somewhere, if the error is zero, or the partial derivative is zero. Then we can add some little amount of noise for it. Some noisy number for the given weight. And giving this noise, keep doing the training. And then this noise, just like at the real annealing, steel annealing, we are giving this noise, this little noise for the given situation, it will shake out a little bit at a given point. And we have a good chance to get some better result. Clear? Interesting, isn't it? Next thing is the very important element, the so-called pruning. If we train the network, and if the network is more or less okay, instead of implement the whole network not into the hardware, when the weight is close to zero, we can cut this out. This is also a kind of heuristic method, the pruning. As we know, in nature, it is very important to have this method to trim the trees and the bushes. If we are not trimming the trees, it will grow as it wants. But if you want to produce some good fruit on it, the gardener should prune it, cut it down what is not needed. The same metaphor used in neural networks too. Prune the network, cutting out the not needed parts. Because if it is close to zero, it won't have any influence anyway. If it is zero, we don't need to do anything with it, we will cut it out. We are not using that. Somehow shrinking the weight matrix. Another method, what is very, very popular these days, so-called pooling. End of this class today, I'd like to show you an interesting, fascinating little video showing the convolution networks, how the convolution neural networks works. Complicated, can be extremely complicated, many heuristic elements in it, but I find a fascinating literature, and you can read it if you like, or you can watch it actually at home if you like. It utilizes pooling, meaning that somehow combining the data and shrinking the size of the weight matrix. Kind of pruning, somehow cutting down. But there is a method how to do that. You will show you soon. See how is that. And then there's another method to do that. Instead of pruning, doing totally the opposite. Incrementally changing the network. Incrementally adding new and new elements in it. You can think what is happening in nature. I think, maybe I'm wrong, but I think basically the pruning is there. Because when we born, we already have all of the neurons in our brain, but we will have the rest of our lives, right? But later on, some of them, sometimes significant part of the brain is disappearing because of the aging, because of natural procedures. Since the brain is fault tolerant, we don't feel much difference unless somebody has Alzheimer's or some terrible sickness. What major part of the brain is somehow gone. If not this is the case, we don't feel difference, even though we are losing some neurons. Maybe our brain will be more efficient, who knows, but still working. And we can utilize this in our neural networks areas too. But there's an alternative, adding more and more neurons. What is the good news, what we just learned as humans some years ago, if some part of the brain is somehow damaged, some vascular situation or some injury or something like that, if the person or the creature who has this brain can live long enough, those brain cells can grow back. Well, extremely slowly, but somehow adding new elements. Something fascinating. And this procedure can be speeded up using the stem cells. Inserting stem cells into the brain or into any part of our body, those stem cells can turn to the brain cells and can be something useful in the future. And we can mimic this using artificial networks. And one of the good examples for this cascade correlation, for this incremental network design, was invented a long time ago. It's called cascade correlation. I brought it here because it is easy to understand. Let me show you what is that. If here are these very simple training sample, we have two categories. One is the red ones, another one is the blue ones. And we want to somehow make some kind of classifier, what we classify between blue ones and red ones. This kind of situation, it is called linearly separable because we can put a line between that. Artificial neural networks are very great for doing this. We can train network to differentiate between patterns. As we learned in the 1950s, they was able to figure out characters, A, B, C, D characters, using just that one trainable layered simple neural network called perceptron. But we learned it had a very hard limitation because it was able to differentiate only this kind of network, this kind of data. But if the situation looks like this, there is no way to put a line inside. That's why the whole research area stopped for decades, especially in the US, when everybody read this the Minsky and Pepper's article about the perceptrons. But later on, when Rumelhart and McClelland and the other person invented the backpropagation, that was able to do something like this, to understand something like this. And if this is like this, we can somehow differentiate between these two spirals. Just lifting these together. If we are lifting these blue ones and red ones, we can put a plane between that. So easy. But the question how to lift it up. They had to introduce hidden layer. And to be able to train the hidden layer, they had to use this backpropagation method. So easy. And another method was this cascade correlation, meaning that if you have a very simple network, for example, having only 2 inputs and 2 outputs, a training sample is something like that, 2 inputs, like in an example, x1, x2, and 2 outputs, A and B. And if you provide blue, the A will be active. If you are providing the red, the B would be active, something like that. And we can train it, because if the situation is different, is linearly separable, this very simple network will do it. We can train it. We can set the proper weights here, going through many of the samples, the training data, and then it will do the classification. There's a special term in this field, classification. Classify it, A or B, making 2 groups. This can do it. But if it is a linear not separable situation, this single layer network will be not able to do that. But we can do something. It's a great idea. These guys invented that long time ago. They put an extra neuron here, connect it to the inputs, and then try to modify these weights here to be able to go the output of this thing parallel to the error. So if these go together, it has a correlation between the output of this neuron, new neuron, and the error function, then we can connect this output to the inputs and use as a cancellation device to cancel the error, to decrease the error. Let me show you how it works. First, connect it to the inputs and train these inputs, the input weights here, to be able to correlate the output of this neuron to the error. And if we have a significant correlation because of this training, we are training only this one. Then we can connect this point to here, and then using this output as a cancelling signal, somehow decrease the error in the network. It sounds strange, but it works fantastically. For example, if we are not happy enough with the result, we can put another input there, train it, and then we have this correlation again. We can connect these to here, and then cancel the error again. We are doing that step by step. We have a growing network, incrementally growing network. And based on this network, we can do classification, even if the data is non-linearly separable. Show you one example of what the students made it long time ago in this school. I asked them the same example what was here, and the data, eventually, this is how the result generated. First, it was so coarse, and eventually it was improving. One important thing what I like to mention here, the neural network has a very interesting feature, so-called generalization. Generalization, meaning that even if the sample was not there, something close what we used, it will still give us some good answer. It is called generalization. As an opposite of that is called overlearning, when we can train or learn only the data, nothing else. We need to avoid somehow the overlearning, because in that time we cannot be sure if the situation happens when the sample was not in a training samples, it will give us a wrong answer. But we still expect some good answer if the given data is close to the training set. So this is the short list of these interesting new ideas. And at the end of this class, I will show you one of them is utilized in a convolution networks too. Fascinating. Since there is a time to have a short break, I like to have a 5 minutes break, and then I will continue with the competitive learning, one of the major branch of the neural networks. Thank you for your attention, and see you back in 5 minutes.